Up to this point, we've talked about one-dimensional problems. We've also talked about time-dependent problems with no dimensions. At this point, we're going to start looking at the semi-infinite solid, which is both time-dependent and one-dimensional. So we're going to be looking at the conduction equation and solving its transient behavior. Now, a semi-infinite solid is a system or a substance that only has one wall. It's infinite in the x direction away from the wall, and it's also infinite in the y and the z directions. That means we only have one heat transfer surface. This is actually a very useful idealization for a wide variety of problems with very short timescales. It's valid for small Fourier numbers for a wide range of geometries. If you look, even a sphere, if you zoom in far enough, looks like a flat surface with an infinite side. So if your time and space scale is small enough, almost every geometry can look like this semi-infinite solid. And then we have three basic surface conditions that correspond to our three boundary conditions, right? We have the constant temperature boundary condition on the surface for t greater than time equals 0. We have a constant heat flux on the surface for time greater than 0. And we have convection on the surface for time greater than 0. And then our initial condition is that everything is at t initial, or ti, including the surface, for times less than 0. So that at t equals 0, everything is equal to ti. As soon as t goes above 0, suddenly we have one of these three boundary conditions applied. And we're going to look at each of these three cases. So the first case is to look at our constant temperature boundary condition. So we're going to use some dimensional analysis to define a similarity variable eta. And eta is a dimensionless variable that's going to be used to characterize both time and position. You can see it contains both time and x here. And to make our math easier, we're going to add this factor of 4 under the square root. It really doesn't have any physical requirement. It's just to make the math a little bit easier. So when we do that, we get the heat equation, which is a little bit different because now we have absorbed the space and time components into eta. We can rewrite the heat equation as an ordinary differential equation just in terms of eta here. And then our boundary conditions are when eta is 0. So if eta is 0, it either means x is 0 or time is infinite. So when eta is 0, t is equal to t surface. So at infinite time, the whole substance will be at t surface, which it makes sense. And then the other boundary condition is when eta is infinity, and this means that either time is 0 or x is infinity. T is going to be equal to ti, which makes sense because at t equals 0, everything is at the initial temperature, and if you're very far away from the surface, then you should still be at the initial temperature. So those are our boundary conditions. Now I'm not going to go through the whole solution process, but the solution to this looks like this integral. Basically what we do is we define dt d eta as f, and then we have first order differential equation. So we get df d eta is equal to negative 2 eta f, and then we get f is some exponential function, and then we integrate that to find t as a function of eta. So this integral does not have an analytical solution. We have to evaluate it numerically, and we call it the error function. So that integral gives us this error function. So the temperature difference between a particular location, t, and the initial temperature is given by this error function, or eta. Now when we take the derivative of the error function, we get this exponential function, and we can find the surface heat flux using Fourier's law. And this shows that the surface heat flux is going to decrease over time. As time increases, that denominator is going to get larger, which makes sense because as time goes on, the surface temperature is going to be remaining the same, but everything else is going to heat up, and that's going to reduce our temperature gradients. So we can convert that from alpha into some of the more primitive variables and get a little bit different version of this solution. We also have some other boundary conditions. If we have constant heat flux, the math here gets a little bit more complex because surface temperature can change over time, so that changes our boundary condition. So the form of the solution is a little bit more complex. I'm not going to go through all the math here, but the basic principle is the same. It's also important to note here this complementary error function, and that's basically 1 minus the error function. It's just the complement to the error function. And then if you have a convective boundary condition, of course, you have another solution. So any of these solutions can be used depending on the boundary condition you're applying. Now, there's actually a pretty interesting case, which is where you have two semi-infinite solids come into contact at t equals 0. And initially, they're both at a different temperature. In this case, A is at a higher temperature than B. If we neglect the contact resistance between them, we assume they have a perfect contact. We have two boundary conditions at that boundary. The first is that the boundary temperatures have to be the same of both. It has to be a continuous temperature distribution. The second one is that the surface heat fluxes have to match. So the heat flux out of A has to equal the heat flux into B. So if we have a constant surface temperature boundary condition, we can actually find the heat flux between the two based on the surface temperature and the initial temperatures. And we can use that to solve for the surface temperature. And it turns out that the surface temperature is actually a weighted average. And it's weighted by this fluid property term, which represents both conduction and heat capacity. So we can look at this and see how two semi-infinite solids are going to respond, what the surface temperature is going to be, and so on.